wrote number 25 up here. So chapter 8 is all about acids, bases, calculating pH, and calculating the concentration as well. So we're going to start by looking at the definitions of acids and bases, because we haven't really talked about them yet. We've actually seen them in some double replacement reactions that we've done before, but we haven't really named them or known exactly what they do. So starting with question 25, we have the Arrhenius theory states that acids produce blank and bases produce blank. So in order to answer that question, you kind of need to know what happens when an acid dissociates. So when I mean dissociates, it's like an ionic compound. It dissociates into its positive cation and its negative anion. So that's what we're seeing here. The acid, in this case, I'm doing a strong acid, which is hydrochloric acid. That's the name of this guy. And when hydrochloric acid dissociates, or when it's dissolved in water, when it's aqueous, what happens is it dissociates into its H plus and Cl minus. So when it says that acids produce, it's looking for it produces H plus, because all acids, according to the Arrhenius theory, the Arrhenius definition, all acids should produce an H plus proton ion. Okay, so H plus would be the answer here. Because this negative portion, that's not the acidic portion. That's not what makes it an acid. That's just the anion portion of it. So now for bases, it says when this sodium hydroxide, which is a strong base, dissociates, it's going to form an OH minus ion. Okay, so bases produce OH minus according to the Arrhenius definition. Now there's another definition of acids, and that's the Bronsted-Lowry definition. And it defines acids and bases a little different. It defines them based off of what they donate and what they accept. Okay, so to look at this definition a little bit more closely, it's best to look at the reaction between an acid and base. So what I have shown here is the dissociation of an acid and the dissociation of a base, like what happens when the ions separate. So what we're going to look at now is what if I reacted an acid with a base, and that'll help us do this definition down here. So I'm going to erase this top portion, fancy paper towel eraser, and we're going to look at adding now HCl plus NaOH. So what would happen here? Okay, well, we've actually done this reaction before, or we should be able to predict it, because this is a double replacement reaction. Okay, now what we call it in this chapter, other than double replacement, so let me write that real quick, double replacement, because we have a compound reacting with a compound and they're going to switch partners. But in this chapter, we're going to also refer to it as a neutralization reaction. So when an acid and base react, they neutralize each other. And what we're always going to see, what always the products are going to be, are water plus a salt. So anytime you're adding an acid and base, doesn't matter if it's a strong acid and a strong base, a weak acid and a weak base, a combo of the two, your products are always going to be water and a salt. So I just said one of the products is water. We have H2O here. And how did we form H2O? Well, I said this was a double replacement reaction. So let's look at that. So for double replacement, we have AB plus CD makes AD plus CB. So that's our general outline of a double replacement reaction. Well, A is H, right? And then Cl will be the B. Over here we have sodium is the C and OH is the D. So instead of writing it like this, let's write it like this. So we have H is the A, put H, and then my D is this OH hydroxide ion. So if I put H and OH together, I get H2O. So that's how I get that product. Let's look at the salt portion. So we said we're going to put C with B. Well, C is sodium, B is chlorine. C comes first, the metal portion comes first always, and then Cl. So NaCl, what is that? Table salt. So water and a salt. Neutralization reaction, acid with a base. So the Bronsted-Lowry, now let's look at what's happening here and how the Bronsted-Lowry definition of an acid and base is. It's saying that an acid, this guy here, acts as a blank donor. So what is this acid donating? Well, it's donating this H+. So it acts as an H+ donor. But what we call H+ in this chapter is we call it a proton. Now, when we say proton, we're not talking about the subatomic particle proton that's present in the nucleus of an atom. We're talking about H+ proton. So it's the same name, but different definitions. So when we refer to a proton, when it comes to acids and bases, we're talking about this H+. The reason it's often referred to as a proton is because it has a +1 charge, just like a proton does. Okay, that +1. So when we say proton in reference to acids and bases, we're talking about H+, not about the proton in the nucleus of an atom. All right, so Bronsted-Lowry defines an acid as a proton donor because it's getting rid of its H+. It's donating it. It's giving it to that OH to neutralize it. Because according to the Arrhenius definition, acids form H+, bases form OH-. Because that H+ is being donated to the OH- to neutralize it so we get water. Because water that we learned in this chapter, if you watched the PowerPoints already, has a pH of 7, and that is neutral. So we're trying to neutralize it by forming water, a neutral compound, okay? So acids donate a proton and bases accept a proton. OH accepted the proton. So that's how we do the Bronsted-Lowry definition. So talking about pH, let's now move into pH. Neutralization reaction, we said we're trying to get neutral, and I just said a pH of 7 is neutral. Well, let's look at where acidic and basic pH levels are. I'm going to do a pH scale off to the side here. For pH scale, we have 7 in the middle. Another room. 8. I think it goes up to 14. All right. So anything below the 7 is acidic. Anything above the 7 is basic. And then right around 7, this small region here is neutral. So this is the pH scale. So the higher the number, the more basic it is, the stronger the base. Okay, the more basic that solution or sample or what have you. The lower the pH, the more acidic it is. So for instance, if you had a pH of 1, that's going to be an extremely strong acid. You don't want to get that on your hands. Same with a pH of 14. That's a strong base. It's corrosive. You don't want that either. Neutral, right around 7, is where we usually have water. And that's where hopefully we'll see most of our samples neutralized right around 7. So how do you calculate pH? Well, I'm going to the equation sheet now. So chapter 7 and 8 equations at the bottom, these last 2 equations we haven't used yet are what we're going to be using in this chapter here. So the equations we have, I'll write those over here and do the problem in the middle. We have pH is equal to -log H3O plus. And we have H3O plus equals, oops, 10 to the negative pH. So here's our equations. Important things to note. What does this mean? These brackets, which is the H3O plus, that's the concentration of the protons. Okay, so the concentration of the acid portion. Sometimes in place of this H3O plus, it might just say H plus. Okay, both of them are the same thing. The reason they have H3O plus is they basically have a molecule of water with an extra proton on that molecule of water. So they both mean the same thing. It's a concentration of the protons in that particular solution. So let's look at number 27 on the homework, on the practice homework, where we're calculating the pH of 1 times 10 to the negative 2 m of HNO3. Okay, so they want us to calculate the pH. I should say question mark. So it says calculate the pH, that's the question. It gives us this number, 1.0 times 10 to the negative 2, with a capital M after it. So what does the capital M mean? That's concentration, molarity. We looked at that, gosh, chapter 6, I think. When we did concentrations in chapter 6, molarity was moles over liter. It was a type of concentration. So they've given us the concentration. So that's our H3O plus in these equations. Since we're calculating pH, we're going to use the equation where pH is equal to. We're going to have pH equal to negative log, and then H3O plus. So this is going to go in there. Now, I can actually predict if it's going to be acidic or basic based off of the compound they gave me. They gave me HNO3. It has H plus ions in it, so I'm going to assume, rightly so, that it is an acid and that its pH should be below 7. Okay, so that's kind of just a double check for when you're doing some of these problems to make sure you're doing the calculation correctly. Oftentimes, people forget to put this negative first, and that's going to mess the whole problem up. So when we're solving for pH, you're going to put negative log, so you're going to press the negative sign on your calculator. Not the minus sign, but the negative sign. It depends what kind of calculator you have. So on mine, I wouldn't push the minus sign, but I'd push this little negative I have in parentheses down here. And then my log function, wherever your log function is, all calculators are different. Right there. And then once you press the log function, parentheses should pop up, and that's where you're going to put the concentration given in the question. I'm going to use 2 sig figs because they had 2 there. I get 2.0, and that's my pH. So way down here. So yes, it is acidic. So if the question asks, would this be acidic or basic, you would be able to answer that as well based off the pH and comparing it to the pH scale. All right, let's look at the next one. So number 28, it is asking us to calculate the concentration. Of a solution of hydrochloric acid with a pH equal to 3. Well, looking at the compound itself, I could tell it's an acid. If it dissociates, it's going to have H plus ions, so it's going to produce H plus. It's going to be a proton donor, so it is an acid. And then also I can tell it's going to be acidic because of the pH. It's way down here in the acidic region by 3. All right, so this time we're calculating the concentration. We are given the pH. So we're looking at this second equation here, where the concentration, which is going to be in molarity. Remember, I told you molarity is the concentration calculation that we use most often in chemistry. So that's why we're seeing it so often. Now on this one, I'm going to do 10 to the negative 3. That's going to give you 1 times 10 to the negative 3rd concentration. So we're going to put a capital M for molarity. Now I'm going to do a harder one where we don't get 3.0 exactly. So I think that was it for the homework, practice homework, but I want to do one more just so I can show you how to enter one of these into your calculator or what functions, buttons you need to use. So let's look at the same sort of situation here. And we'll just say a solution, and I'm not going to give you a compound. So we're going to figure out based off of the concentration given to us, comparing it to the scale to see if it's acidic or basic. So let's say the pH is 8.25. So it's not a whole number this time. Okay, so the pH is 8.25. Comparing it to the scale, slightly basic, right? So I know it's basic. Now I want to see the concentration. So looking at it, we're doing the same equation we just did last time. Negative, and then we're going to put the 8.25 up here. Now this time we'll actually have to enter it into our calculator to figure out the answer, because we don't want to put the answer like this. We want a whole number, not a decimal number there. Okay, so to enter that in my calculator, for mine, it's going to be different for everyone. I have to press the second button and then log function. Okay, the reason I do this on my calculator is because I'm looking to use the 10 to the x portion. So when I enter second log, I then want to put a negative sign with my 8.25 there. So go ahead and try this on your calculator to make sure you're using the right function and getting the same answer. My silly calculator never puts it in scientific notation for me. So I'm going to go ahead and do that myself. So to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the negative 9th. So now notice, this number is a lot smaller than the previous number because this is telling us the concentration of H+ ions. So last time when we were looking at an acidic solution with hydrofluoric acid, we got 1, I'm going to compare the last question, 1 times 10 to the negative 3rd. So this is just 0.001 molarity. So this was the concentration of the hydrofluoric acid, right? Now let's compare it to the concentration of a basic, because we just said 8.25, it's slightly basic. Notice the concentration of the H+ ions is much, much smaller because of this -9, and it should be, because the less H+ we have, the more basic it's going to be. The more H+ coming from the acid part of the problem, so the more H+ we have, the more acidic it should be. So if the concentration of H+ is higher, it's going to be acidic. If the concentration of H+ is really, really low, it's going to be basic. Okay, so it's just a check on your work, making sure when you're doing a comparison.